As an internal project about 7 or 8 years ago, but the company itself is only been around for 2 years, Volta Insite that is. We started in the oil and gas, in downhole motors specifically. The issue there was a lot of times you may have a motor failure, but you'd like to preemptively understand when that failure may happen. They had tried a couple of projects with putting electronics in the actual motors themselves, and the electronics would fail before the motors because of environment. And the beauty of the Volta Insite system is that you can deploy CTs and voltage taps up at the top of the surface in the electrical room and get an understanding as to how the motor is behaving. So we'll get into that in a little bit. Any electrical people in the audience? Perfect, so we'll take it easy. About 100 years ago, there was a big fight between AC and DC. Our friend Nikola Tesla won the fight because with AC, you have the ability to go from low voltage to high voltage using a very cost-effective piece of equipment called a transformer. And then you're able to transmit power for long distances with high voltage and ultimately bring that voltage down on the receiving end with another transformer. So when we talk about power quality, the key is on the generation side and then on the distribution side, we want to ensure that we have steady voltage levels, steady voltage levels and frequency without interruption. So how do we generate the voltage? We have a generator, and this is an oversimplified version. We have 3 coils at 120 degrees apart, and ultimately we spin a magnetic field within that generator, creating 3 phases of voltage and current that are 180 degrees apart. So in order to have good power quality, we need minimum amount of voltage sags and swells. We want to keep the amount of transients within that voltage to a minimum. And obviously we don't want to have any power interruptions. Additionally, we want low harmonic distortion, so if you have a lot of VFDs within a facility, you can actually feed back into your own distribution switchgear and create problems there. And you want to have frequency stability and balanced phases, but in industrial applications, balanced phases are less of a problem. So why is it important to maintain good power quality and eliminate ghost electrical problems? Because if those create catastrophic events in terms of your equipment, it's not necessarily even the cost of the equipment that's expensive to replace, it's the downtime associated with the lost equipment that's more expensive. So on this page, we talk about light manufacturing, $200,000 an hour, up to energy producers, maybe $2 million an hour. And that's what we're trying to eliminate. On voltage stability, maintaining a steady voltage at all times is important. There are 2 ways that you may have a voltage problem at a particular load where you're actually using that voltage to do work. One is a utility variation that happens, and that's completely outside of your control. The other is within your internal distribution system, you may have something that's acting up, like a fuse disconnect, a breaker that's bouncing, and those are things that you can actually look at and understand and try to eliminate before they become problematic. Example of voltage instability. This is within your own distribution system at the facility level. So this is an example of a contactor starting to go bad on a motor. I think this specifically was a starter. Yes, it's in the writing. And you'll notice at the beginning of the day at around 6 a.m. we start detecting these voltage anomalies. By mid to end of day, we start having single phasing events. And if those events go for long enough periods of time, you will actually single phase the motor and ultimately have a catastrophic event. So by continuously monitoring these systems, you can actually, you can actually trend over time the anomalies and how bad they get, and be able to create a predictive action to fix the problem before it becomes catastrophic. Here's another example of a voltage transient, and this is specific to a facility at the utility end. So there's a voltage variation that happens, and that voltage variation creates a big current spike within the facility, and that may throw off the equipment within it, also creating downtime, even though it may be temporary. Here's another example of voltage variations that happen from the utility side specifically, and it has to do with the utility trying to keep up with demand. This is an example of downtown Toronto. You'll notice that the voltage is around 600 volts during the start of the day, and towards the end of the day, you're dropping below 585. This is important, especially in Canada, because we think that a 600 volt system is sufficient to buy equipment at 575 volts. So if the utility is allowed to vary the voltage plus or minus 10%, on the positive side, you will end up burning motors. So understanding what the utility level is, what the utility is actually giving you is important. This is an example of harmonic distortion within a facility. This is a facility that has a lot of VFDs. The VFDs create a lot of switching noise and effectively put harmonics back in the distribution system. And you'll notice in this case, the voltage is no longer purely sinusoidal, it's slightly off. This may not be a problem for the majority of equipment, but it could have some effects. So how do we eliminate this problem? Well, in my opinion, I believe the first thing to do is effectively monitor your equipment, your critical assets, as well as the utility, to understand if there are ghost electrical problems within your facility, to be able to diagnose problems quickly. There's also frequency shifts that may happen, and that's usually a direct consequence from the utility. A lot of it has to do with renewable energy sources and some big heavy loads where the utility can't handle it. And then there's balance phases, and this is more on the commercial side. So how do we monitor to understand what is happening? We have this node hardware and VI module hardware, where VI could stand for voltage and current. Wrong button, sorry. The node itself gets deployed on the outside, on the outside of the switchgear, within an electrical room, on the side of the switchgear. It is a data acquisition device. It does 20 kilohertz of sampling or more. The VI module sits within the switchgear or fuse disconnect or motor control cabinet. The VI module is also paired with CTs, and the CTs are connected to the VI module, and then we need some voltage taps. This allows us to monitor the complete power being delivered to the motor and the voltage. So it acts as understanding what the load is doing, as well as power quality monitoring. With InsiteAI, we're able to connect to the cloud, and whenever we see transients and events, we will send out a notification to our customers to tell them exactly what is happening and interpreting the waveforms. Because we're also cloud connected, we can give you engineering support on the back end, and we get the alerts first, and we are able to send out alerts to our customers and give them some guidance as to what prescription to perform. Now, if you're monitoring power quality continuously, you're able to also perform this concept of electrical signature analysis. In the simplest form, this is a circuit which tells us that the voltage will always be produced from the source and the load will always consume current. So if you are able to demodulate voltage from current, you can understand exactly what is happening on the load side. So here's an example of a compressor with a two-pulley system and a belt. If we do a continuous waveform capture of the current, we can actually plot that in the frequency spectrum, and then we can go look at the harmonics, and specific harmonics are associated with very specific faults. So in this case, we're pointing to 0.903 of LF, where LF is the line frequency of 1. And if we look at this harmonic over time, we're able to identify that the belt is getting looser or something is happening with a tensioner. So this is the concept of electrical signature analysis, and all the harmonics, if you have a gearbox and so forth, I'll get into some more examples, are associated with a particular current signature. One additional note is that we normalize the harmonic spectrum with regards to line frequency. That's why it's 1. Traditional aspects of electrical signature analysis either use 50 hertz or 60 hertz. This is useful in the application of VFDs. When VFDs are running at multiple speeds, now you can have a basis to actually trend all the harmonics based on the actual gearing associated with that system. So this is an example of an elevator loose belt. Specific harmonic is 0.71 of line frequency. And you'll notice back in April of 21, we had baselined the system, and over time this starts to trend upwards. We send an alert to the facility guys go check it out. Yes, indeed, we've got a loose belt on our hands. They perform maintenance, and the harmonic comes back down to baseline. Here's another example of a fan. In this case, we had baselined this particular harmonic. We start jumping all around. Turns out that the fan itself had a lot of debris built up on its blades. They scheduled maintenance, they took the fan down, they cleaned the blades, rebalanced it, and we're back to baseline. Lastly, this is an example of a gearbox. We had baselined the actual gearbox over a period of time. We saw harmonic jump up. This was maintenance performed. So in this particular case, we didn't have the geometries associated with the gearbox, but we were able to have a discussion with the facility and say, well, we've noticed this harmonic. They went and replaced a specific sprocket. The baseline came back down. The next time the sprocket, the harmonic associated with that sprocket started to rise, we sent them a notification. They performed maintenance, and we saw the actual harmonic come back down in amplitude, but then suddenly rise once again. We alerted the facility, and it turns out the guys who did the maintenance accidentally put the wrong sprocket hardness in it. And so when they figured that out, they replaced it with the correct sprocket, and we're back down to our baseline. So that's the beauty of electrical signature analysis. In conclusion, being able to measure continuous waveforms at 20 kilohertz, all your voltage and current, I think is really important. It gives you an understanding as to what is happening within your facility. Ghost electrical problems can be a thing of the past. And then electrical signature analysis can be leveraged on top of that if you're doing this continuous waveform monitoring anyway, to be able to eliminate any type of catastrophic downtime ultimately.